Hello, it's Keith here, and this is lesson 58 of the platform-specific series of my Z80 programming tutorials. We're going to be going back to the Sam Coupe today, and we're going to look at the other screen modes that the system possesses. We looked at the 16-colour screen mode before, which is the best screen mode from the fact that it's the most powerful, but there are some other ones that are really interesting and definitely worth having a look at. Before that though, I'd like to point out I have an extra domain name now, chibiakums.com. It's going to stay there, nothing's changing, but it's a bit hard to type on your phones and remember. So you can now go to learnasm.net at the bottom of the screen, and that will take you straight to a list of all of the systems and all the tutorials I cover. You can also get there with assemblytutorial.com as well, which I'll be using more soon as well. So please bear those in mind if they're easy for you. Anyway, so we're going to be looking at the Sam Coupe again and these extra screen modes. So the main screen mode, the mode 4 that we looked at in the past, it's 256 by 192 at 16 colours, and that is a 24K screen, which is quite big. It took up a lot of memory, a little bit difficult to work with in some ways. There are some other screen modes. Mode 3 is a 4-colour mode. It's twice the horizontal resolution, so it's 512 by 192, and it's still 24 kilobytes, so that would be your word processor mode possibly. Very, very nice mode there, very high resolution and 4 colors. We've also got a mode 1, which is exactly the same as the Spectrum. It has the flashing bits, it has the bright bit, and it has 8 foreground and 8 background colors. We can, however, configure the foreground and background colors using the entire Sam Coupe palette though, so that is a bit of a bonus. Now, in between this, rather strangely, there's a mode 2. Very much like the MSX1, we have a 256 by 192 bitmap where each line of 8 pixels is stored in a single byte, of course, foreground and background. But we also have a color map where each color is defined by a single byte for the same 8 by 1 pixel sort of oblong. Now, the thing is, unlike the MSX, which used 4 bits, 1 nibble for each color for the foreground and background, on the Sam Coupe, it actually mimics the same Spectrum format, where there's a flashing bit, a bright bit, and there is 3 bits for the background and 3 bits for the foreground, so exactly the same as mode 1. But this is quite an interesting idea in that it gives a lot more color potential, and again, we can reconfigure the colors, so a lot better than mode 1 on the Spectrum mode, but also a lot less memory than mode 3 and mode 4, so possibly worth bearing in mind, because the MSX1 does have the ability quite often to throw out some quite impressive color screens because of its superior color attributes compared to the ZX Spectrum. Okay, so we've got a brief summary of all the modes here because they were a little bit tricky for me to figure out, so hopefully I'll be able to help you out and save you a little bit of time. So mode 4 here, 256 by 192, 16 colors, 2 pixels in each byte of the screen, and it's in a linear format going across the screen and then down. It's no weird layout, fortunately. And if we map the video RAM bank to the 0 position, it would start at quadruple 0 to 5 FFF, a 24 kilobyte screen there. Now there's no color attributes because the color pixels are defined at the pixel level, so it's just a very simple format. That's the first mode 4. Mode 3, we're doubling the horizontal resolution, 512 by 192. Just 4 colors per pixel, and that means that there's 4 pixels per byte. Now the leftmost pixel is the top 2 bits of the byte. The next pixel is the next 2 bits. It's in a linear format across the byte, so very straightforward, not anything as weird as the CPC there. The screen size is the same, so quadruple 0 to 5 triple F if mapped to the low memory area. And so that's mode 3. Now we'll skip mode 2 for a moment and go for mode 1. Mode 1 is 256 by 192 again, and there are 2 colors, a foreground and a background, for each 8 by 8 tile. There's 8 pixels per byte because it's essentially black and white, with 0 defining the background color and 1 defining the foreground color in the bitmap area. And the pixel data is from quadruple 0 to 17 FF. Now that's 6 kilobytes, and as well as that we have the color data. This is defined at the 8 by 8 pixel area, so an entire character block on the Spectrum. And this will allow us to define a foreground and a background, and a flashing option and a bright option. And you can see the layout that the bits in that color data will be defining. Now that's at 1800 to 1B00 for mode 1. Now that's exactly the same as the Spectrum, and I believe also it reconfigures things like the clock speed on the Sam Coupe. I'm not quite sure on that, but I think there are some other changes that occur when you turn that mode on, so it really starts to clamp the system down to really be a Spectrum. And I think it's a bit of a waste of the Sam Coupe's potential in some ways because it's got much better color screen options. But as I say, we can, however, configure the colors, and we'll see how we do that later on. Now the final option is mode 2. and this is a kind of enhanced version of that. We've got the same 256 by 192, the same 8 pixels per byte, and the same pixel data at quadruple 0 to 17 FF, but we now have another bank, exactly the same 6 kilobytes. This actually starts at a different position, starting at 2000. There's a 2 kilobyte gap, which I didn't figure out for a while, misreading the documentation, so bear that in mind. It's a 2 kilobyte gap, and this defines the colors for each 8 by 1, 8 pixels across 1 pixel tall strip of the screen. And so effectively we can define the colors for every single byte, a different foreground and background color, and this will give us strips of individual colors potentially. As I say, a lot more potential than the ZX Spectrum gave us, but even with the Spectrum compatible mode we can change the colors. So that's what we're going to be looking at today. So let's go over to the source code and let's see all that in action. Okay, so here's today's example. Now the first thing I'm going to do is I'm just going to fire them up and we'll actually see the code running, so we can see all of these screen modes. Now this code actually has sort of various sections that will turn on and off depending on the mode we want to run with. So let's first of all fire up mode 4. This is the 16 color mode. And here you can see the palette hasn't been set, so the colors are a little murky, but this is our Chubico character. It's a 16 color screen, but we're only using 4 of the 16 colors for our character because this has been transferred from things like the Amstrad CPC. That's the character there. So you can see that's been represented there. Now, if we change this to mode 3, let's remember this mode 3 definition here, we're now running some different code, and you can see it's become half the width, and that's because we can now have 4 pixels per byte in the 4 color mode, and because we're only using 4 colors, the character looks exactly the same. Okay, now going to mode 1, the Spectrum compatible mode, you can see our Chubico character is just there, and to just show off the color attributes, I've done this kind of checkerboard effect. Each of these blocks is a different set of color attributes, so the background color has been alternated between yellow and a kind of blue here, and the foreground is purple in all cases there. So that's the mode 1. And then the mode 2, which as I say is this kind of weird mode, we've got, it's a bit messed up, but here it is the Chubico character. And so I've set the top strip and the next strip to alternating blues, but then in this area in the middle, oh, can I make this bigger? Yes, I can. Hang on a minute. In this bit in the middle, I've changed colors every single byte, so you can see these kind of thin strips, and hopefully you can see that this is 8 pixels wide and just 1 pixel tall, and that's the definition that we can define the color attributes at if we so desire. So that's what we are able to do here. Now we're going to go over the code that does this, but of course we do need some sprite data to match. Now in the example here, the format for the 16 color mode is actually the exact same as the MSX for 16 color mode. The 4 color mode is exactly the same as the MSX 4 color mode, and the other 2 modes were basically a black and white bitmap, which is the Spectrum. Now the color attributes I'm storing separately, but you can export all of these with my AccuSprite editor. If you go to ZX80 and you go to Sam Coupe, I've currently only got this save raw bitmap, which is the 16 color option. I'm going to put the 4 and black and white options in there as well, but the code's actually already there because it's literally the MSX options. So I just haven't, and the Spectrum options, I just haven't put in the links yet into this copy. But it would be save raw bitmap here. That would do it for the black and white screens. So as I say, I'm going to put it in. I just haven't got around to it yet because I was writing this tutorial quite late yesterday. So we're going to get that in there. But as I say, you could already do it just using the alternate menu options there. So our bitmap data is being imported and is in the correct format. So what do we actually have to do to turn these modes on and to use them accordingly? Well, let's start with modes 4 and mode 3. Let's just select mode 3 here. So the first thing we need to do is we need to select the screen mode, and we do this with port 252. You can see that all of these options here, depending on which is defined, is loading the accumulator with a different combination of bits. You can see here that these are defining the video bank, the bank of memory that's going to be the video display. These are selecting the screen, and the top one is relating to MIDI. We don't need that. So it's these 2 bits here that are defining the screen mode. So mode 4 has this set to 3. Mode 3 has it set to 2, mode 2 has it set to 1, and mode 1 has it set to 0. I nearly got that the other way around. So that's the 2 bits that we need to define to change the screen mode, and then we need to send that to port 252 here. Now you will notice we're disabling interrupts here, and you'll also notice that the code is address 8000 here, and that's important when it comes to making this code work and banking in the memory. You see, banking unfortunately on the Sam Coupe works in 32 kilobyte chunks. You can't bank in a 16 kilobyte chunk, you have to bank a 32 kilobyte block in one go. And because our code is 8000, that means we're having to mess with the zero range, which is why we've disabled interrupts. So just bear that in mind. You might want to do things differently, but that's the way my tutorials are configured for compatibility with other systems that 8000 tends to be free on. So that's the way I do things. So once we've selected the screen mode, we then need to page in the memory here, and we're doing that here. We're just selecting the same bank that we selected here, and we're setting that to the low memory area from 0 to 7FFF here. We're defining a new stack pointer because I think the old one would have been in that range, so that would have broken calls and things. And then this code is going to be used on every single system. We've got get screen pos, which we've seen before in the bitmap series. So that's selecting the screen address 10,10, 10 across in bytes and 10 down in lines. And then we're going to draw 48 lines of our sprite, which is the included file you saw a moment ago. And we're just going to copy all this data to the screen, and we're going to move down the screen a line with whatever code we need to do that, and we're going to repeat. So we're going to need a get screen pos command and a get next line command for our respective screen mode. And these are down here. Now, this is the one for screen modes 4 and mode 3. The screen is 128 bytes wide, and so we just multiply the Y location by 128, and then we add the X, and we would add any offset, but the screen is offset to 0, so we don't need to do that. So that's calculating the screen position from an XY coordinate, and then to move down the line, we just add 128 hexadecimal 80 here, and we had to add any carry to the top byte. You'll see we're using DE here as our destination, because that's what LDIR uses. So that's the very simple modes 3 and mode 4, pretty straightforward. Now mode 1 is very tricky. You can see all this nastiness here. This is in the exact same format as the ZX Spectrum, so I literally copied this code straight off my ZX Spectrum tutorial. So I'm not going to go into it here because you can go and watch the ZX Spectrum tutorials on the simple bitmap series or my other bitmap example on using ZX Spectrum. But this will calculate the rather odd screen coordinates of the ZX Spectrum because it splits the screen into 3 and it's kind of interlaced in a way. It's quite inconvenient for calculating locations, but this will do it for us. So this will calculate a screen location and move down the line. Now we also have that color information, which we're going to do separately. So this will calculate the color location address, and this will move down a line. Now the color information is in a linear format, so it just goes across the screen for 32 blocks because there's one block for each 8x8 pixel area of the screen, so there's 32 across, and then each line is consecutive after the last one, so we just add 32 to move down a line. And you can see that our color information is being drawn to the screen with this section here. This is what's doing it, and we're loading in a fixed value pretty much here. So this is the starting value, but we're just XORing it here. The bottom 3 bits here will be the foreground. The next 3 bits just here will be the background, and the top 2 bits are the flashing and the bright. The flashing is annoying, but it does work. We can prove that, I suppose, if I just put that one there. And you can see we're flipping the background color with these 3 bits here. If these 3 bits were on, we would flip the foreground. So we're just setting all of the areas after we've calculated the screen memory position within the memory that we need to set. And I'll just enable that here. And you can see we've now got this horrible flashing thing here, but we asked for it, so we get what we deserve. But as I say, that does indeed work, and it works even with interrupts disabled, which is quite curious. So that's the mode 1 code, and of course we do have the mode 2 code as well. Now, where's the mode 2 code? Where is it? I can't find it. It's very straightforward, really. Unlike the Spectrum compatible mode, the mode 2 is in a linear format, so it just goes across the screen, down to the next line, and it carries on. I don't think it's based on anything else that I know of. It's similar to the MSX1, but as I say, the color information, the color attributes are basically copied off the Spectrum, so they don't match the MSX1. But as I say, it's a nice idea. It's a good trade-off with regards to memory. 24 kilobytes is a very big screen to be hulking around, whereas if you have a screen of just 12 kilobytes, that doesn't get in the way of your 0 area where you might want your interrupt handlers and things. So it's a good trade-off if you need a fast screen and you can trade off the colors. But as I say, so our address calculation for the a screen location XY is we multiply the Y by 32 because there's 32 bytes per line, and then we add the X and we would add the base, but the base is 0 here. And to move down the line, we just add 32. Now, when it comes to the color information, we do need to provide color information, but we don't actually need another command to do it because the calculation is so simple it would have been a bit silly to do so. So all we're doing here is we are basically adding hexadecimal 20 to the calculated address because the colors start from hexadecimal 2000 onwards, and the format is exactly the same as the bitmap data because there's the same number of bytes for the colors as for the pixels. So as I say, we just need to either add hexadecimal 20 or in hexadecimal 20 here. And as for our palette, well, we've got this bitmap I've defined here, test palette. So these are the first two lines. When I say lines, sorry, that's not right. That's 8 pixels tall and the entire 48 pixels wide. So that's a kind of spectrum style color strip. But then we're defining the next bits here at the individual strip level, because remember each color attribute here is just going to be 8 pixels wide and 1 pixel tall. So I'm defining them here, and that's giving that rainbow middle area. And as I said before, the format is the same as the spectrum. So these are the foreground colors, these three are the background, that's the bright bit, and that's the flashing bit. Okay, we'll just get that enabled and we'll run that again. It is enabled. So there we go. And as I say, you can see those very, very high definition color attributes in this middle area here. These crude ones just here, these very thick ones, are these definitions just here. Now that's how we can get colors onto the screen. But what about actually changing the color attributes? Because as I said, the spectrum and that sort of MSX mode, they are a bit more powerful than before. We can actually change the colors so we aren't stuck with the spectrum palette. Well, to do that, we just set the Sam Coupe colors. And if you remember, all we need to do that is we load BC with a byte pair, because the Sam Coupe uses 16-bit ports. Now we load the bottom byte C with F8, and we load the top byte with the color number we want to change. So 01 to 0F effectively for the 16 definable colors. So if we want to define color 1 here, we just set this F8 and this here, and then we can define a red, green, blue color attribute here. And so here we are defining this as bright green, I think this is. So I should have put this in, but here's the format of the color definitions: green, red, blue top bit, a light bit which increases the brightness of all colors, and then green, red and blue bottom bits here. So if we wanted to set the dark color 1 to magenta, what we would do is we put a 0 here, set red and blue to maximum, we'll set the light bit on as well, and if we run this now, there we go, we've got a nice bright magenta, which of course the spectrum could have done anyway, but you get the point. We could put a 1 there, and now we will end up with a paler magenta, that's a pale pink there, and that's how we set what would effectively be the dark color 1. But if we want to set the colors for when the bright bit is enabled, because remember we're mimicking the spectrum color information, we would use color 9, because color 8 would be the equivalent of the black when the bright is enabled, which you could actually now set, which doesn't do anything on the spectrum. But it's to say we can set these colors as well. So if we just try setting these to hit 1 here and we compile this, you can now see that yellow has become much brighter. And alternatively, if I set 8 here, you can see we've now set the bright black, if that's a thing. We've set bright black to that yellow now. So we do have a lot more control, and this does make the spectrum color attributes have a lot more potential. And this is similar to something the Spectrum Next did, of course, because the Spectrum Next also allowed you to reconfigure the colors of the classic Spectrum mode there. Okay, so that was a pretty quick introduction there. I think we've gone over the basics of how those modes work. Of course, you can download today's source code and give it a go, you know, if you want to try it out yourself. What I'd suggest is to say, once you've got an idea of it, it shouldn't be too hard for you to work with these modes. So try it out, download the source code, and hopefully you can make use of these if you feel they're going to benefit you for your game. Well, there we go. That's all we're going to be covering today. Hope you found this interesting. I hope you'll give the Sam Coupe a go and try out these new interesting modes, because they were certainly new and interesting to me, with the exception of the Spectrum one, which I'd seen before, of course. But impressive set of colours, and it really does show the potential for the Sam Coupe. It's got a lot of the same abilities of the MSX2 with regards to its screen modes, but it's much easier to work with because the memory is mapped within the normal Z80 memory rather than having to use ports and special commands and things. So as I say, definitely something that I'd suggest you take a look at if you are looking to do some programming on these 8-bit systems. Anyway, I hope you've liked this. Please like and subscribe if you had. And please check out my forums, because I've got some chat forums on my website for discussing assembly programming and other retro stuff. But whatever you do, please enjoy the Sam Coupe and programming in general. Thanks for watching today, and goodbye.